Great to present this talk at FunQCD 2021. We're going to present our recent monographic work on the lattice flavor-singlet QQQ variants that are of interest because their position in the spectrum is a consequence of the existence of the color degree of freedom in the underlying theory.
Around 1964, Gell-Mann and Neyman noticed that baryons could be arranged in representations of flavor SU3, such as the octet here depicted. The constituent interpretation of such diagrams is that three quarks recouple their flavor up, down, or strange to yield one of the wave functions that appear in them. Notably absent is the singlet baryon representation. It would sit in the center of the octet diagram here, having the same quantum numbers, but it is nowhere to be found in the ground state spectrum, and this is because of color. Let us show this.
The baryon wave function has a part assigning the internal quantum numbers, color and flavor, and a part determining the external quantum numbers, spin and orbital angular momentum, and radial-like excitations. Our understanding of color is that its wave function is always the antisymmetric singlet. This is confinement. No colorful representation has ever been found in a variant, and our best theory indicates that it will never. Next, a flavor singlet is also in an antisymmetric configuration. But because quarks are fermions, the total wave function has to be antisymmetric. All three things, antisymmetry of the total, the color, and the flavor wave functions, require that the spin spatial part also be antisymmetric, and this excludes ground state configurations and S-wave.
Indeed, looking at the experimental spectrum of UDS lambda baryons, we see that the several candidates that people have discussed, the black and red lines in this plot, lie several hundred MeV above the ground state octet, here the zero of the y-axis.
If you want to see the actual masses for those candidates and theoretical calculations, you may want to pause this video here and look at this table. Which of these variants could be the flavor singlet?
A possibility is to carefully measure the experimental branching fractions. Here are two simple computations shown in our article for positive and negative parity respectively. If you want to test that a certain baryon will be the singlet, you need to fix its mass on the OX axis of either, and sliding along one of the vertical lines, you can read the decay pattern for that mass. Experiments should match these flavor-symmetric chiral type computations at the 10% level to ascertain whether the singlet pattern would emerge. Experimental precision is for now insufficient.
To see what actual quantum numbers are possible, we construct the wave functions in detail. Highlighted in yellow is the orbital angular momentum part, in orange the spin part, and in green the radial part, to which we dedicate the next slide. We find these three possible combinations with only one quantum of excitation, as is known from earlier studies of the grass or bond groups.
We use the variational principle applied to the Hamiltonian in the next slide to estimate the mass. We have tried several families of variational wave functions, as shown here. The best results were obtained with a hydrogen-like one and with one that rescales the exact numerical solution of the two-body problem with the same Hamiltonian.
The Hamiltonian has three main pieces. The one-body piece includes kinetic energy and quark mass. This will be dynamically enhanced by the running dynamical mass upper right corner plot generated upon solving the gap equation in BCS approximation.
Confinement is implemented in the Coulomb gauge longitudinal potential among color charge densities. We use the parametrization by Swanson and Szczepaniak.
We also include a transversal potential among charge currents, with a Yukawa-like potential reflecting the gluon mass gap. This different treatment of longitudinal and transverse gauge degrees of freedom is typical of a Coulomb gauge formulation.
Let us just flash for the record what our computer code actually has to deal with. Once the trial wave functions have been selected, we calculate a multidimensional index, weighing them with a spin-dependent kernel that comes from the Hamiltonian.
This is done with a Monte Carlo sampler. The computation is repeated for each set of variational parameters, and we find a broad minima. Given the overall complexity, we have checked the whole setup with two well-known variants with simpler flavor structure. The ground state omega mass comes right on. The delta variant turns out to be a bit too heavy, but this is expected of three quark computations that disregards open channels, in this case binuclear.
And finally, here are our computed masses. We look for the minima in the corresponding variational surfaces for each set of quantum numbers. We have found that the lightest singlet QQQ baryon configurations can have spin parity 1/2 minus or 3/2 plus, with a mass of about 1.7 GeV or so. Because the lightest experimental candidate is at 1.4 GeV, We are convinced that it is largely a meson-nucleomolecular configuration, and not an intrinsic 3-quark state. This would have to be found among the higher mass experimental candidates.
In conclusion, because of color confinement, we do not expect a flavor-singlet baryon in the ground state. How highly excited it is can be used to test more detailed models of color interaction. We have carried out a variational computation in a field theory model of Coulomb gauge QCD that respects its global symmetries and found about 1.7 GeV. The experimentally low lambda 1405 does not look like a good candidate. To confirm that one of the experimental candidates in that mass region is indeed a QQ flavor singlet. More detailed experimental data on the decay Brentzian fractions is necessary. Check our article in Physical Review D for more detail.
Thank you for listening.